Hello students, in this video we are given this network where a switch is given which is closed at time t is equals to 0 here, and we have to find expression VCT and ICT for t greater than 0. Okay, so first we will see what happens to this capacitor or the voltage across this capacitor at time t 0 minus, or we can say before switching. When switch is opened, so at time t less than 0 we will find the value of this, and this will remain same as VC0 and VC0 plus because of the property of this capacitor. It doesn't change its status immediately. So this capacitor will behave as a open circuit since it is connected to this battery since long time. So voltage across this is nothing but VC, and we have to find this value VC 0 minus, or VC you can say here, that is equals to a current would be flowing here when it is opened, that is 5/3 ampere multiplied by this resistance is 1 plus 1, that is 2. That will give us the voltage drop VC, and it is equals to 10/3 volts. So it is our initial condition or the voltage across capacitor. Now we will see our circuit at time t is equals to 0. At time t is equals to 0, this capacitor is again part of our circuit and this switch is closed. Okay. Now at t is equals to 0, this is our network, and at t greater than 0 we have to write KVL to find these expressions. But our circuit is little complicated. First we can see that these resistances are connected in delta connection. So we will first convert this delta into star network to simplify the circuit. Okay, this is 2, 1 and 1 ohm. Convert this into a star network like this. Okay, so the way to convert these two into this is branch of star is 1 into 2 divided by the sum of all, that is 0.5. Again 1 and 2 and divided by sum, that is again 0.5 ohm. Okay, and the third is 1 into 1 divided by 4, and that is 0.25. So our simplified or our star to delta transformation transformed circuit will look like this. This one circuit, this one resistance, another resistance and third resistance. Here will come our battery, here is capacitor, another resistance 1 ohm, this is 0.5 ohm, this is again 0.5, this is 0.25 and capacitor of 1 farad and battery of 5 volts. Okay, this is circuit after converting this star into delta into star. Now we can see that circuit is not that much simplified, as we can easily apply the KVL in the circuit. So we will convert this circuit into its Thevenin equivalent. Okay, leaving this capacitor, we will convert this whole circuit into its Thevenin equivalent. Okay, so representing the network on left of capacitor by its Thevenin equivalent. Okay, so here first we will open circuit this capacitor and we will find VTH here. So VTH is voltage across this, and since no current is flowing, so VTH is nothing but the voltage at this node. We can find it easily because one current would be flowing, and that current is 5 divided by 2, that is 2.5 ampere current would be flowing here in this circuit, and drop VTH is nothing but 2.5 multiplied by sum of these two resistances, that is 1.5, and it is equal to 3.75 volts. So our VTH is 7.5 volts. So here VTH and in series with a resistance RTH will come in our Thevenin equivalent circuit, and here we will connect the capacitor. Okay, the capacitor which we removed from here, that will come in series with this. So 1 farad resistance. Now after finding this, we will find RTH. RTH is resistance across these terminals after short circuiting this source voltage, independent source voltage. Okay, so here this resistance is in parallel with this resistance, these two resistances. So 0.5 is parallel to 1.5, and it is in series with this 0.25, and that will give us RTH. Okay, after solving this, 0.5 into 1.5 divided by 2, that will give us 0.375 plus 0.25 will give us 0.625. 0.625 ohm is our RTH. So RTH is 0.625. Okay, and this we will connect this capacitor in series. So this is our Thevenin's equivalent. Now we can apply KVL, KCL very easily to find VCT. VCT is nothing but voltage across this capacitor. Okay, so we can apply KCL here. So one current, suppose one current is flowing in this direction, and take all the currents outward of this node. Okay, so here this current is, this voltage is VC. Okay, so VC minus, and this voltage is 3.75. Minus sign will come because we are coming in this direction, and the later sign of this voltage source is this, divided by 0.625 is equals to current across this, which is flowing again outward in the outward direction. So sum of this C dVc by dt, and our C is 1 volts. So this is our equation, differential equation, which we can write here like this: dVc by dt plus Vc divided by this, that is 1.6 Vc plus, sorry, minus this 3.75 divided by 0.625 is nothing but 6. So we can write it like this. So this is our differential equation, and its solution can be written, if our differential equation is like this: dV by dt plus PV is equals to Q, then its solution is VT, or you can write it here VCT, that is equals to e to the power minus PT. Here the P is 1.6, so write down 1.60 integration e to the power PT. So here P is 1.60 multiplied by Q, and our Q is here, this is the value of Q, 6. Okay, so multiplied by 6 dt plus second term K multiplied by e to the power again minus PT, and P is 1.6T. So this is the solution of differential equation which gives us expression VCT. Now we will solve this first term, that is e to the power this. So this will come up equal to e to the power minus 1.60 multiplied by e to the power plus 1.60 divided, since it is integration, divide by 1.6 here multiplied by 6. So this is our first term. This will be cancelled and will become equal to 1, and 6 by 1.6, that is 6 by 1.6, that is 15 by 4. So the first term is 15 by 4 plus k e to the power minus 1.60. This is expression VCT. Now we will find the constant k with the help of initial condition. We know the initial condition, that is VC0 minus is equals to 10 by 3. So put t is equals to 0 in this equation. So VC0 is equals to 10 by 3. Okay, we can see there from initial condition is equals to 15 by 4, and t is equals to 0 will make this equal, e to the power 0 is equals to 1. So here we can get the value of k. K is equals to 10 by 3 minus 15 by 4, and that is equals to minus 5 by 12. K is minus 5 by 12. Okay, substitute this value of k here, that is minus 5 by 12. So this is the expression VCT for this given network. This is 5 by 12. Okay, now we have to find expression for this ICT. We know the formula, that ICT is, and relation between ICT and I and V is ICT is equals to C dV by dt. Okay, so we can find this value ICT simply multiplying this VCT with C and differentiating this. So C is nothing but 1. Now differentiate this with respect to t, this whole VCT. Okay, differentiate this whole VCT, that is 15 by 4 minus 5 by 12 e to the power minus 1.6 t. Okay, that will give us the ICT. Differentiation of this first term will be 0, and differentiation of this second term is 5 by 12 multiplied by minus 1.6, and this will remain as it is 1.6 t. Okay, so here we can get two by 3. Okay, 2 by 3. So 2 by 3 e to the power minus 1.60. This is the expression ICT. So here we got both the expression, the voltage across capacitor and the current through capacitor at time t greater than 0 by using these few steps. Thank you.